Okay, so to remind you, we covered special relativity very, very quickly. And we had this quantity eta mu nu. And then we went on to consider some quantity g mu nu, which is a function of space-time. And as I mentioned, the role of eta is to define geometry on Minkowski space-time. Geometry on Minkowski, so we use it to discuss lengths and times and so on. And this, of course, discusses geometry on a general space-time. Okay, so to give you a better picture of what geometry is on a general space-time, let's consider a simple example. And because time is more complicated, I'm going to just do space. Time always introduces this minus sign. But let's think about a spatial geometry. And what's the simplest curved space you can think of?
Sphere.
Sphere. Okay, so let's discuss a sphere. A two-dimensional sphere. Okay, just like the surface of the Earth, roughly. And how do we define a sphere? How would I define the space? How would I define the space, a spherical space? What equation do you think you'd write down? X squared plus y squared, right? So let's one consider embedded in R3, which is a space of 3 coordinates. So we can visualize it in this room. And what we'd write is just x squared. Oh, I'm using that notation. X squared equals 1. And this, of course, is x squared plus y squared plus, in fact, I'm going to call it x1 squared plus x2 squared plus x3 squared. Okay, just x squared plus y squared plus z squared equals 1. So that's obviously a sphere. And here it is. And this is x3, x1, and x2. Drawn very badly. Okay. So the point of describing the geometry of a space using a metric, the main point is to describe it intrinsically, to get away from the idea of embedding. After all, you know, if you're an ant that lives on the surface of the sphere, you really aren't going to care about what's inside it or what's outside it at all. All you care about is what you see within the sphere. And so the question is, can you describe the sphere, what we call intrinsically, using quantities which only live on the surface of the sphere? So intrinsically, so instead of using 3 coordinates with a constraint, can we describe it using 2 coordinates? Okay, so what do? I say x1, I use polar coordinates, the usual polar coordinates. So from the z-axis, the polar angle theta, and then I have the rotation angle phi. Okay, so every point on the sphere corresponds to some value of theta and some value of phi. And so what I do is I satisfy this constraint by writing x is sine theta cos phi, x2 is sine theta sine phi, and x3 is cos theta. right? So obviously x1 squared plus x2 squared, I get cos squared plus sine squared, which is 1. And so that leaves me with sine squared. And then when I add x3 squared, I automatically get 1. So this kind of trick is used everywhere in the study of curved geometries. And so now we can say, what is the metric? How do I measure distances within the sphere? Okay, so imagine I have these 2 points. First of all, let's imagine them very near to each other. And how do I measure the distance from one point to another in the sphere? Or alternatively, if I've got 2 tiny vectors on the sphere, how do I measure the angle between them? Okay, I need to take the dot product. I need something to let me do that. In this space, I have a metric, right? Just dx squared plus dy squared plus dz squared. In this space, in the R3, I have Pythagoras. Okay, that tells me the length squared between 2 points in the embedding space is just dx squared in the embedding space. And that's Pythagoras. And actually, as you learn quantum mechanics and general relativity, what you'll realize is that Pythagoras is at the heart of both subjects. Okay. Essentially, in quantum mechanics, you calculate psi star psi. That's the probability. It's the sum of squares. And it's normalized to 1. And all quantum evolution is motion around a sphere, preserving the probability. In general relativity, this Pythagoras comes in when you define lengths at short distances. Okay? So locally, that sphere looks like a 2-dimensional flat surface. I can draw a tangent plane to the sphere, and if I don't go very far, that's quite a good approximation. So let's take the distance squared of the embedding space, which is just Pythagoras' rule, and of course figure out what is it in terms of the sphere. Right? So all I do is I plug these formulae into here. So dx1 squared plus dx2 squared plus dx3 squared. That should be the distance between 2 neighboring points. And if they're both constrained to the sphere, they will both be described by formulae like this. And I can just differentiate. dx1, right, so I just do the obvious thing. dx1 is cos theta d theta, cos phi, plus, minus sine theta d phi, sine phi. Right, just differentiating. Do the same with all of them, square it, add the squares, and you get d theta squared plus sine squared theta d phi squared. So I'll just leave that to you to check. And that is the metric on the sphere. So this is equal to gij dxi dxj, where xi equals, the coordinates on the sphere are equal to theta and phi. And I goes from 1 to 2. Okay, I've not used terribly good notation because I'm using x in both cases. I'm happy to change this to y if you like, just so you don't confuse it. So I've gone from 3 coordinates on the sphere, where I know one of them is redundant because I never go outside the sphere. So I go to 2 coordinates, which is theta and phi, and then I write down the metric. And that's what it is. So this metric is a 2x2 matrix, right? So the gij is 1 in the theta direction, 0 on the off diagonal, and sine squared theta over there. Okay, so we call this the induced metric on the sphere. It's the metric induced from the embedding metric. Because that's how I got it. I got it by inferring it from the Pythagoras rule. In the higher dimensions. Now, question. Are these r, theta, and phi good coordinates on S2? Are they good coordinates? What do I mean by good coordinates? Coordinate, what's a good coordinate? I've mentioned this before. Got some space, and I label it with coordinates. You know, you draw your coordinate lines, like on a map. Good coordinate system is where every point on the space corresponds to one value of the coordinates. 1 to 1. Is that true with the theta and phi? No, they're lousy coordinates. Okay? Why? Because the lines of constant theta are circles, right? Lines of constant phi, these are the lines of longitude, right? These are the phi equals constant. But there's some problem with the North Pole and the South Pole. Big problem, okay? Namely, this North Pole is theta equals 0, phi equals anything. Actually, just to be more precise, obviously we know that theta goes from 0 to pi. Theta equals 0 is the North Pole, theta equals pi is the South Pole. And phi goes from 0 to 2 pi with 0 and 2 pi identified. Okay, because phi equals 0 and phi equals 2 pi is the same point. So that's okay. You can have some coordinates which are defined on this compact space, a circle. But this is really not so good, that phi is anything from in the interval 0 to 2 pi. So these 2 points, phi equals anything, the map from the space to the coordinates is 1 to many. So they're really bad coordinates. Okay? So now a map from S2 into theta phi is 1 to many at the North Pole and the South Pole. So a very big deal when we come to do general relativity is to pick a good system of coordinates. If you pick lousy coordinates, you get all sorts of disasters in the theory. So it turns out there's, in a sense, an ideal coordinate system would be one which is just 1 to 1 everywhere on the space. Turns out there are topological reasons on the sphere why that's impossible. It's actually impossible to write a coordinate system on the sphere which is 1 to 1 everywhere. So what you have to do is use different coordinate systems to cover different parts of the space. So, for example, in this case, we could use this set of polar coordinates, which is bad at the North Pole and South Pole. But I could equally well choose a set of polar coordinates defined on 2 other opposite points, right, and use them as well. So when I'm describing, let's say, the other polar coordinates are here have singularities, those 2 points. So if I'm describing something around here, I would use these polar coordinates. And something here, I would use, something here, I would use the original polar coordinate. That's okay. So you have to keep going from one coordinate system to another. There's nothing wrong with that because the equations are designed precisely to allow you to go between coordinate systems. But it turns out there's a better system of coordinates, and I'll show you it just because it's fun. And these are projective coordinates. Okay, so the definition of these coordinates is very geometrical. You imagine your sphere as being intersected by a plane running through its equator. Okay? And of course, this plane is two-dimensional and flat, and has two coordinates. Let me call them, well, let's leave them as that for the moment. The plane has two natural coordinates. And then the idea of projective coordinates is you stand at the North Pole, for example, and you look at some point on the sphere, and you just draw a straight line from you through that point to intersect the plane. And so this will be the coordinate of the point on the sphere. Okay, so you stand there with a torch, you shine it through, and the torch hits the point on the sphere and then goes on to the plane, and you say, aha, that's my coordinates on the sphere. Now, can you immediately tell me where are the singularities in that coordinate system? At the North Pole. Why? Because if I stand here and I shine my light on a neighboring point, it's only going to hit the plane at infinity, right? So the North Pole is going to be mapped to infinity. Somewhere near the North Pole would get mapped to a very large radius. Somewhere at the North Pole, it's really mapped to infinity. So indeed, there's a singularity here. Are there any other singularities in this coordinate system? No, right? Because I can go down here, I can shine my torch on a point here, and it'll just map to some point inside this unit disk on the plane.
So you're on the sphere shining the light, or you're on the plane shining the light?
You're at the North Pole shining the light.
Okay.
So there are North Pole projective coordinates, and there are likewise South Pole projective coordinates. Right? So I could stand at the North Pole and shine my light to hit the point, P, and then this point P goes to a value x1, P, x2, P. These are the two coordinates of the point P on the plane. I should write it as, well, I'll just write it at x1, x2 for the moment. Now, it's not hard to work out the formulae for these coordinates. Let's imagine, so I'll draw it like this. Let's imagine we're standing at the North Pole, and imagine the point we're looking at is lies on this circle corresponding to x2 equals 0. Okay, so that's a particular case where the point is where I just slice the sphere this way, and the point is on that circle. It's just easier to see the geometry in this case, and it'll be straightforward to generalize. So consider a point. Consider a point at phi equals 0, or on the circle, on the great circle. Phi equals 0. So when we draw these lines here, this one is phi equals 0, and this one is phi equals pi, and then as we go around, phi equals 2 pi is the same as phi equals 0. Okay, so here's the point. I'm going to project it onto the plane, onto some value of x1. Okay, so obviously this distance is x1. The height of the point is x3. And by these, I'm using the same embedding coordinates. These are the embedding coordinates. Yeah, I've been a bit confusing. Yeah, let me label these n now. These are the projective coordinates. these are the embedding coordinates. Okay, and so x2 is 0. So the coordinates of my point are x1 and x3. x2 is 0. Now when I do this, you can see this distance here from the North Pole to the down the axis to x3 is 1 minus x3, right? And then this distance here is x1. This distance here is x1. Okay, so if I want to know what is the coordinate on the plane, this is x1n, how do I get it? We have a triangle up here whose sides I know, 1 minus x3 and x1. Then I have a triangle here, which I know this side of is 1. So what's that side? I want to know what is x1 and how do you do that? Speak louder. Similar triangles. Yep, they're similar triangles. They have the same angle. This is horizontal, vertical. This line is obviously the same line. So similar triangles tell you that that x1n over 1 is equal to x1 over 1 minus x3. Okay, so obviously x1n equals x1 over 1 minus x3. Now, does that make sense? The North Pole is x3 equals 1, and x1, x2 are both 0. So as x3 goes to 1, x1n, the coordinate on the plane, is going to infinity. Okay, so that makes sense. What about if so I've picked a very special point, which lies on this plane, x2 equals 0. What if I rotate this around? Okay, so if I just do a rotation on x1 and x2, I rotate x1 into x2, it's clear that wherever I rotate it, it's just the same thing, but rotated, right? So exactly the same picture, but where I've rotated x1 into x2. So in general, to generalize to arbitrary x1 and x2, and what we get is that x1n equals this guy is just x1 over 1 minus x3, and x2n equals x2 over 1 minus x3. Okay, because x1n and x1 both rotate in the same way, right? So the case I considered was x2 equals 0, both for the embedding coordinate and for the projective coordinate. But this is the general case. So those are projective coordinates on the sphere as represented in terms of the embedding coordinates. Likewise, we have South Pole projective coordinates constructed in exactly the same way, but where the torch is held at the South Pole. And can anyone tell me what these formulae are? x1s equals and x2s equals. Remember, the North Pole coordinates are singular at the North Pole, where x3 is 1. The South Pole coordinates are singular South Pole, where x3 is minus 1. Obviously, they're related by x3 goes to minus x3, right? Because it's just flipping the north to the south. So all you do is x1 over 1 plus x3, x2 over 1 plus x3. Okay, so those are the north and south pole projective coordinates. And now what about the metric? Oh, we can express. So we have two sets of coordinates. We have north and south coordinates, and in fact, we have a relation that x1 north is x1 south over x1 south squared plus x2 south squared. And x2 north is minus x2 south over x1 south squared, put these brackets here, plus x2 south squared. And, sorry, there's no minus there. And in the metric, the x squared, that's the dx1 squared plus dx2 squared plus dx3 squared, is equal to 4 dx1n squared plus dx2n squared over 1 plus x1n squared plus x2n squared. There's actually another squared in there. Yeah, this is squared. Okay, so that's the metric in North Pole projective coordinates. You notice it looks, I mean, if you look at the metric in spherical coordinates, spherical polars, theta equals 0, theta equals pi, the metric seems to have a problem, right? Because when theta equals 0 or pi, the sine squared theta is 0. The metric is not invertible. Remember when we used eta, it's very important we had eta and its inverse. The metric is not invertible at theta equals 0 and pi, and that's related to the fact the coordinates are singular. Here, things look much better. I mean, the only place the metric is problematic is where the x1 and x2 are at infinity. So there's only one singularity, if you like. Point at infinity, it's singular. And we can also write this in terms of South Pole projective coordinates, and it should be obvious by construction the whole thing is symmetrical. So these are just two different expressions for the metric in the two sets of coordinates. So that's just another coordinate system on the sphere. And in different applications, it's useful to use these different sets. This is a less singular set of coordinates because each one of them is only singular at one point. So in general, we need a number of coordinate systems to fully describe a curved space. And the number depends on the topology. So obviously a sphere has some interesting topology. If you make the topology more and more complicated, you may need more and more coordinate systems to describe it. A picture we often draw is if I have some coordinate system x, which describes part of the manifold, and by that I mean, locally there's some set of coordinate lines in one-to-one correspond. Each coordinate is in one-to-one correspondence with the space. And then I may have some other coordinates, x prime, in which has some different set of lines. And then, of course, I'm going to have to do the transition in between the coordinate. Where the two coordinate systems overlap, I have to understand how to relate objects in one coordinate system to those in another. And I may need three coordinate systems, for example, x double prime. And then these three coordinate systems will overlap in some common area. And so, in general, we need to ensure consistency in overlap regions. For example, if I went from x to x prime, the x primes are functions of the x's, and the x double prime will be functions of the x primes. And I need to make sure that x double prime of x prime of x is the same as x double prime of x. Okay, and when I come to consider tensors and how they transform, I'll need to consider that tensor quantities, which are transformed by going from x to x prime to x double prime, equal those where I transform from going to x to x prime. X to x double prime directly. So these triple overlap conditions are actually very important in some situations. Okay, so we have all these coordinate systems. We have to live with them because the only way we know how to describe geometry is in terms of numbers. But at the same time, we know these coordinate systems, none of them is particularly preferred to any other coordinate system. And we just have to get used to using them and keeping in mind the fact that there's nothing fundamental about any particular choice of coordinate systems. Now, I want to go back to something I mentioned before at the end of last lecture, which is imagine I have some space and I consider the geometry locally near some point. So with a sphere, it's very clear that if I'm really near to some point, I can pretend the sphere is flat. Okay, and basically if the distance I go from this point, if x is much less than the radius of the sphere, then the sphere looks flat. Okay, and that's the reason human beings thought that the Earth was flat, right? Until whenever it was, until somebody started sailing a ship far enough, and the view changed. People thought they were living on a flat table, and they were very worried that the sea would fall off the edge of it. And what was going on the edge of the table? So the first maps made, actually, do you know who made the first map? Who's the person who made the first map? See, we don't remember these amazing things. Somebody called Anaximander in ancient Greece made the first ever map, and it was very Greek-centric. Okay, and it included Greece and then a little bit of Africa and part of Europe. And it was in the shape of a circle, because looks like the horizon. And they had no idea what's beyond the horizon. So they thought space was flat, and who knows what happens, at large distances. But then another Greek actually did some measurements and figured out that the location of the sun on the sky changes in angle depending on your latitude. Went to Egypt and did some measurements, so it got a different angle, and from that figured out the radius of the Earth, and so figured out it's actually curved. So obviously he had to go some distance to see the change, because he's living on a curved surface, not a flat one. Okay, so to come back to this, let's ask a question from the reverse point of view. So given some g mu nu of x, if somebody just hands you 4x4 matrix, which is a function of x, and tells you that describes the geometry of the world you live in, can I change coordinates to make g mu nu of x approximately equal to eta mu nu in my neighborhood? Okay, so we have this infinite freedom to choose coordinate systems. Can I pick coordinates so that locally it looks like Minkowski space? The geometry looks Minkowski. And that calculation is very instructive, and it's actually the calculation Riemann did modulo the minus sign in the eta. It's the calculation Riemann did in 1820 or something. By the way, when he was a PhD student. Okay, and he figured out the answer is yes. You can change coordinates so that space looks locally flat, like in this. And he also worked out what is the measure of the deviation from flatness. And it turns out the deviation depends on the second derivatives of the metric. You can always set the first derivatives of the metric to 0. The second derivatives you cannot. And the extent to which you cannot is the Riemann tensor describing the curvature of the space. So let's do that calculation. So the answer, yes, Riemann, I think 1830-ish. And it's quite instructive to see how you do the calculation. So we're going to assume g mu nu of x is differentiable. Okay, so in general, we call a curved space a manifold. And if it has a metric which is differentiable, we call it a differentiable manifold. This is differential geometry. So assume this is G is differentiable. If so, then it has a Taylor expansion that it's equal to G mu nu of 0. And I'm going to choose my point, the point I'm at. So let's choose coordinates in which I am located at x equals 0. There's nothing special about that. It's just the algebra will be very much easier. If I assume I'm located at some arbitrary constant coordinate value x naught, then when I write a Taylor expansion, the x naught is going to appear, or this particular x will appear everywhere and just muddy all the formulae. So I'm just going to assume I'm at x equals 0. I'm a very self-centered individual, okay? And so let me center my coordinates on me, but I still have an arbitrary number of coordinates. Okay, so G mu nu is equal to the metric exactly where I am, plus g mu nu comma lambda at 0 x lambda plus g mu nu comma lambda sigma 0 x lambda x sigma plus dot dot dot. There's a half in here as well. Where does that come from? What's that called? A certain kind of series? What's that kind of series? Where I take a function and I expand it around some point. Taylor series, just the Taylor expansion. But it's in many dimensions. It's in 4 dimensions in this case. It's just the Taylor expansion in D. D equals the number of independent coordinates. So Taylor expansion in D variables, right? So x mu would be x0, x1, up to x d minus 1. So if I'm in 4D, I've got my time and then 3 space coordinates. Okay, so that's just a Taylor expansion, and any function which is differentiable, you can expand in that way. So the function at a nearby point is just the gradient times the displacement. And then if you're in many dimensions, you must just be careful to sum all those contributions. Okay, and then this is the quadratic contribution in the displacement. So just a Taylor series in all 4 coordinates. Now, we would like to, the idea is to choose different coordinates in which we actually set this guy to 0. Can I choose different coordinates, x prime? So can I choose a function x prime alpha of x such that the such that g mu nu of 0 equals eta mu nu. That's the whole point. I want to set g equal to eta at the point g prime mu nu at 0 prime, the origin in the new coordinate system, is eta mu nu, and g prime mu nu alpha at 0 equals 0. And the answer is you can. You can always find coordinates in which the metric is eta and the first derivative is 0, and we'll just prove it now. So to prove it, we use the following. If x prime is a function of x, that means x is a function of x prime. Right? There must be one-to-one map from x to x prime, likewise from x prime to x. And the metric in the new coordinate system, g prime mu nu of x prime, is equal to, let me write it, yeah, that's right, g alpha beta of x times dx alpha dx beta dx prime mu dx prime mu. Okay, that is a transformation law in going from one coordinate system x to the other coordinate system x prime. Now, clearly, to calculate this, what I need is x as a function of x prime, because I need to calculate these Jacobian matrices. Now, x as a function of x prime, what is that? Well, let's use Taylor expansion. And again, I'm going to do a coordinate transformation where the point 0 goes to 0, because I want to keep myself at 0 in both coordinate systems, just to make the algebra easy. You can change this, but it will just make your life complicated. So I want to keep myself at the origin. And so what is the most general coordinate transformation I can do, again, as a Taylor series? Well, x as a function of x prime to first order in x prime. So we're going to assume x prime is small. Could be that, where K is an arbitrary constant matrix. Arbitrary constant matrix. Okay. So I'm just doing a Taylor expansion in this function around 0 with the assumption that I want the point x prime equals 0 to go to x equals 0. So then there would be L alpha gamma beta x prime gamma x prime, I called it delta, delta 1/6 m alpha gamma delta lambda x prime gamma x prime delta x prime lambda plus dot dot dot. So we assume the coordinate transformation is itself a Taylor series in x prime. We're assuming x prime is small, so this will be accurate. We'll do everything as a power series in x prime. And obviously, k alpha gamma is equal to dx alpha dx prime gamma at x prime equals 0. And L alpha gamma delta equals d2x alpha dx prime gamma dx prime delta evaluated at x prime equals 0, etc. So it's really just a Taylor series, and these coefficients are nothing but the derivatives of the coordinate transformation at x equals 0. Okay, now we have everything we need. We can substitute this expression for g into here. We can substitute this expression for x into all of these x's. We can calculate dx dx prime, that's these factors. Everything is a power series in x prime. And we have everything we need. And we'll get a bunch of equations, and we have to see, can we solve those equations? Okay, so we will get, using 1 and 2, using 1 and 2, this is a series in x prime. This is a Taylor series. And what I'm going to see is, can I set the first term in the Taylor series to be eta, right? For the g prime, I want the g prime to be eta when x prime is 0. And I want the first derivative to be 0 when x prime is 0. And I'm going to then be interested in the second derivatives. How many of those can I set to 0? Or can I set the second derivatives to 0? So we've got quite a few parameters to play with. All of these are arbitrary, right? The k, l, and m are arbitrary, except for some symmetries. You see this guy is symmetrical under these two indices, because that is automatically symmetrical. So I have a whole bunch of parameters to play with in this coordinate transformation. So, first of all, let's look at x prime equals 0. So we look at this Taylor series. Let's look at the coefficient of x, the first coefficient. Coefficient independent of x prime, the term independent, first coefficient in the Taylor series. First term, let's call it the first term in the Taylor series, independent of x prime. Okay, and we can read it off from these expressions. Okay, so I put the g in here. I want the term when x prime is 0. When x prime is 0, x is 0. So I can ignore all of these guys. I just want the first term in this g prime expansion. So that comes from, so g mu nu prime of 0 is equal to, obviously, g mu nu of 0, because x and x prime are both 0 at the same time. And now I need these derivatives. So this is dx prime at x prime equals 0. So that is k mu, so let's do this carefully. This is alpha beta. This is k alpha mu, k beta nu. That's the relationship between the metric at the point in the new and the old coordinates. So can I set this equal to eta mu nu? In other words, is it possible to find a matrix K which will transform this metric to eta? So can I solve this equation? Okay. So, and the answer is yes. This equation in matrix form, we write this as K transposed G of 0, K equals eta. I want to solve that equation. Let me just discuss this transpose bit. Again, it's a little bit confusing. Why do I need the transpose? When I multiply two matrices, I've got to think of one index as the row and one as the column, right? So here I'm multiplying G alpha beta. This is the column beta. I'm contracting with beta in this term. I can think about this as the row, and this is the column. So that's a normal matrix multiplication, row times column. And this index, if this one is a row, well, that one's also a row. That's not the normal matrix multiplication. Okay, so what we do is we say K transpose alpha mu is equal to K mu, let me see, I guess I want it this way, alpha mu. Okay, so I just transpose the indices. And so, so this product of where G is multiplying the K this way, I think of that as K transpose times G. Then it works. Okay, so you can either use this transpose notation if you like. The thing to always go back to is this formula. This transpose is not very useful if you have more than two indices anyway. So, but it's, you know, if you just don't want to write the indices, if you have 2 by 2 matrices, if you have symmetric, if you have matrices, if you have tensors with two indices, it's kind of easier to write it this way. But don't be confused by the transpose. Okay. Now, we look at this matrix. We can always write, so can I take any symmetric matrix and conjugate it with another matrix to make it diagonal, minus, plus, plus, plus. Minus, eta is minus 1, 1, 1, 1, with zeros everywhere else. So can I do that? And the answer is you can. It's very easy. What you say is that K is equal to an orthogonal matrix times L, where L is a diagonal matrix. Okay, so, and the diagonal matrix we'll choose to be diag 1 over, well, let's do the orthogonal one first. So you know very well that because G is symmetric, there always exists an orthogonal matrix that makes it diagonal, right? So O transpose G, there exists an O such that O transpose GO is equal to a diagonal matrix okay, and I'll write it as follows. L0 squared, L1 squared, L2 squared, L3 squared. I'll explain this in a moment. These are zeros, so it's a diagonal matrix. Why did I put 1 minus sign and 3 pluses? Because the fundamental assumption of general relativity will be, so this is a fundamental assumption, is that G mu nu of x has one negative, so it's a symmetric matrix, is a symmetric matrix with one negative eigenvalue, and 1 and 3 positive. Eigenvalues. So what it's saying is that locally the space is flat, like that plane on a sphere, and in that flat space, one direction is going to be time-like, and 3 are space-like. And that's how that assumption enters. Okay, so because of this assumption, when I diagonalize G, one of the eigenvalues will be negative. I can always write it like this, where L naught is a real number, and the others will be positive. Therefore, I can write it like this. So Riemann, in Riemannian geometry, made the assumption that all of the eigenvalues are positive, because he was interested in spaces that are locally Euclidean, locally flat space, in Euclidean coordinates. When Einstein came to do general relativity, he didn't want that. He wanted that locally, space-time should look like Minkowski space. So it has 1 minus and 3 pluses. This is sometimes called pseudo-Riemannian. The pseudo is the assumption that one of the eigenvalues is negative. Okay, so with that assumption, we still have this matrix L, so we've got K transpose GK is equal to L, the diagonal guy, times O transpose times G O L. This is equal to L, some diagonal matrix, times this L0 squared, L1 squared, L2 squared, L3 squared, times L. But these are diagonal matrices, so all we do, how do I set this equal to, how do I solve this equation? What L do I need? It's got to be diagonal, and its only role is to get rid of those L squareds here. So what should I choose L to be? It's diagonal, so it's only diagonal elements multiplying. What L do I choose to make this term equal to minus 1? 1 over L naught. Okay, if we choose L equal to 1 over L naught, 1 over L1, 1 over L2, 1 over L3. Okay, so we've explicitly constructed the matrix K, which will take the metric from being some arbitrary symmetric matrix with the right sign for its eigenvalues into the Minkowski metric. Okay, so we conclude there are enough parameters in K to set an arbitrary G mu nu to eta mu nu at the point x equals x prime equals 0. So we've just done it at one point. Changed coordinates, and our metric is Minkowski at that point. Is this a surprise? Not really, because G alpha beta has how many parameters? If I have a 4x4 matrix, just write down an arbitrary 4x4 symmetric matrix. How many free parameters? 4x4 symmetric matrix. 10. 4 on the diagonal, 6 off the diagonal, because it's symmetric. So 10. Okay, so an arbitrary matrix G has 10 parameters. How many parameters in K? 16. 16 parameters in K. Well, it's 4x4. It's got 2 indices, 4 each. There's no particular symmetry. 16 parameters in K. So it's strange. I seem to have more parameters than I need. Right? So I can easily set G equals eta. What are the other 6 parameters in K?
Lorentz transformations.
Brilliant. Lorentz transformations. So even when you've set G equal to eta, you've got a lot more freedom to play with. You just do a Lorentz transformation of your x. And that'll leave G eta alone anyway. Right? So there are 16. There are only 10 here. The 6 free parameters, or 6 parameters are not fixed by this procedure, are not fixed. And these are the Lorentz transformations. These are 3 rotations and 3 boosts. So the Lorentz group includes ordinary rotations. There are, that's a 3-dimensional group. And the boosts, there are 3 different directions you can boost in. And so that's a 3-parameter group as well. Okay, good. So all this seems to make sense, but we're not done yet because we want to do more. We don't just want to set G prime equals to eta at that point. We want to see, can I set the first derivatives of G to be 0? So that G really does look like eta to a good approximation. And clearly, the parameters I have to play with are those L's. I've used up my K's. Now I need to use L's. So the next question can I set G prime mu nu, comma lambda of 0 equals 0? I probably didn't say that. I should emphasize this. What does this mean? This means d by dx lambda of G prime mu nu, d by dx prime actually, x prime. Right, so comma lambda means differentiate with respect to x lambda. The index is downstairs. It's always when you differentiate, even though x has an upstairs indices, dx is underneath, so it has a downstairs index. And so we write it with just a comma. Using the parameters L. In L, in that matrix L up there, L gamma delta. So to see this, all I do is go ahead and calculate it. So let's do it over here. So again, using a good old chain rule. Can you see here? Is that all right? G prime mu nu lambda at 0 is equal to, so what I'm going to do is imagine sticking the expansion for G, equation 1, into formula 3. This G prime equals G. Okay, so I'm going to put that 1 into this position. I'm then going to calculate this Jacobians using these and express everything as a series in G prime, and then look at the first term in that Taylor expansion. So I'll just write the answer. You can easily check it. G alpha beta comma delta at 0, K delta lambda, K alpha mu, K beta nu. See if we can see where that one comes from. So I put this into here with the x being x prime, and I have my G prime of x prime. I differentiate with respect to x prime. Obviously, I'm going to differentiate this term in the x prime, giving me a k. But also, when I calculate dx prime, just from here, this is going to give me a k as well. Each of these give me a k as well. So I get 3 k's. In addition to this, I have the metric at 0 times L alpha mu lambda K beta nu plus K alpha mu L beta nu lambda. Let's see where that one came from. The dx prime gives me dx prime gives me this term, the k. It also gives me the L times x prime, right? So I get something L x prime on the right-hand side here. But I've got to differentiate this G with respect to x prime to get the left-hand side. So that's going to eliminate the single x prime multiplying the L. So I'm going to get the second term. So it's not a lot of algebra, just to check that you get these terms as well. Now, the question is, I've already fixed my k's, right, by setting G equal to eta. So the k's are now fixed in terms of O and L. There's a little bit of freedom left, the Lorentz transformations, but the k's are essentially fixed. The question, can I solve this equation? The question is, can I solve G mu nu comma lambda prime 0 equals 0 for these parameters L? These are the only things I have to play with. The k is fixed. This was given. Is there enough freedom in the L's to solve this equation? Now, the first thing you should do is just count parameters. How many parameters have you got in the equation which you're trying to solve? So this is an equation for these parameters. Do I have do I have the same number of equations as parameters? If I have more equations than parameters, I generally can't solve. If I have less equations than parameters, or equal, then I can generally solve. So let's count the parameters. Well, how many of these quantities are there? G is a symmetric matrix. So we have G prime mu nu comma lambda, this is symmetric. So it has d plus 1 over 2 components. Okay, symmetric matrix, that's how we get the 10 actually. 4 times 5 over 2 is 10. But in general D, there will be D values of this index and well, D on the diagonal, and then dd minus 1 over 2 off diagonal. And you add them up, you get dd plus 1 over 2. You can also do it using Young tableau, as we discussed. It's a symmetric matrix. I put D in this box. I put D plus 1 in this box. There's one hook, which is 2, goes through 2 boxes, so you get D plus 1 over 2 independent components. And then I have this index, D values. So together, we have D times D plus 1 over 2 equations. All right, these are this many equations. L. How many components of L? Well, L is symmetric under mu and lambda. So this is symmetric. This takes D values. So we obviously get D times D plus 1 over 2 free parameters. Okay, so we have exactly the same number of parameters as the number of equations. Sounds great. We fix all of them. Okay, generically, you can solve and fix all of them. So this is what Riemann realized, is that the first derivatives, you have exactly the right number of freedom in coordinate transformations to remove the first derivative at a point. How do you actually solve it? I mean, you have the right number of parameters, but can I actually solve that equation? In fact, we've done it already. Previous lecture. Remember we had this funny trick where you took an equation with 2 terms and you added and subtracted the same equation with the indices flipped? It's exactly the procedure you need to solve that equation for L. Okay, so I invite you to go through it. It's Riemann's trick. And exactly the same procedure will solve for L. Because we have exactly the same thing. We have an equation in 2 terms. And we just want to solve in terms of one of them. So in fact, Riemann's trick from last time is exactly what you need to solve for L. The manipulation needed to solve for L. Solve explicitly for L. There were some assumptions in that manipulation, one of which is that you can invert the K. But the K, by definition, is an orthogonal matrix times a diagonal matrix. Both of those are invertible. The orthogonal one is automatically invertible. The diagonal matrix, the L0, L1, L2, L3 are, by definition, non-vanishing. So they're invertible. So everything is fine. Okay. So let me end with the final point. So we've succeeded in setting the first derivatives of G prime to 0. So somebody less brave than Riemann might have thought, oh, well, the second derivatives will be the same. You can set the second derivatives to 0. And maybe also the third derivatives, maybe everything. You've got so many parameters here, maybe you can just set everything 0. Set all the derivatives. But Riemann said, no, I'm going to calculate the second derivatives. Okay, and see what happens there. So now we calculate G mu nu prime, comma, nu, come alpha beta at 0. Same thing, but I differentiate twice. Now, it's not hard to see that when I do that, what's going to come in is this guy, the m, which will give you nightmares, how many components it has. Okay? But this 4-index thing comes in. Why does it come in? Because you've got the dx dx prime, which is going to reduce this to x prime squared. But then I'm taking two derivatives of the g prime, right? So I take this g prime, I take two derivatives, respect to x prime. That'll remove two more powers of x prime. I'll be left with m in the equation. So this is an equation linear in M. So you can write it all out if you like, or you can just do the parameter count. Right? So I'm not going to try to explicitly solve this equation at all. I'm just going to count the parameters. So that, which is very interesting. So first of all, we should understand how many equations do we have, right? So I know I've got d plus 1 over 2 independent components of the metric. This quantity is symmetric under alpha and beta, right? Because partial derivatives commute. So this also gives d plus 1 over 2, right? So what I have is d squared d plus 1 squared over 4 equations. How many m's do I have? The m's, well, let's write down, put their indices. Alpha, gamma, can't remember what I called it, delta, lambda. Now, obviously, this is defined to be the third derivative of the coordinate transformation. So these are symmetric because the partial derivatives commute. So there are d indices here. And how many independent components does it have? Well, we draw the Young tableau. There are 3 indices. So this is d plus 1, d plus 2 over, and the hooks, there are 3 and 2. Over 6. Okay, so we have d squared, d plus 1, d plus 2 over 6 parameters. Okay, so the number of components of G mu nu, comma, alpha beta equals d squared d plus 1 squared over 4. And the number of parameters are these. So we have a certain number of components of G where we don't have enough parameters to cancel them, right? So it's easy to see this number is less than this number. Okay, we just don't have enough parameters. So number of components of G which cannot be cancelled equals the number of independent components minus this number of parameters, d squared, d plus 1, d plus 2 over 6. And if we work that out, it is d squared minus 1 over 12. And so that turns out to be the number of components of a new tensor, the Riemann tensor measuring the curvature of space-time. Okay, so if we work in d equals 1, there are 0. So in one dimension, a one-dimensional geometry is just a curve. A curve can't have any intrinsic curvature. There's just length along the curve, and there's no way of knowing if the curve is curved from within the space. In d equals 2, we have 1. D equals 2, there is one component, one second derivative of the metric that cannot be set 0. And so that's saying that there is one quantity measuring the curvature of the space. In d equals 3, there are 6. 9 times 8 over 12 is 6. And in d equals 4, which is the dimension we live in, there are 20. So the Riemann tensor has 20 components. There are 20 second derivatives of the metric, which you cannot, in general, set 0 by a coordinate transformation. And so next time we're going to explicitly construct this tensor, Riemann tensor, and check that indeed it has 20 components. And if it's non-zero, no coordinate transformation will ever make it 0. And those quantities measure the curvature of space-time. Okay, sorry I went on a bit long. Are there any questions? I've battered you into submission. Yes.
So the extra parameters relate to like these types of transformations that we can do, right? What?
Yeah. So we have all of these parameters to play with, but we see even with that freedom, I'm unable to set all the second derivatives of the metric to 0. I just don't have enough coordinate freedom to set all of those quantities to 0.
Right. So for that, for the freedoms and G, what is it, G mu nu, that relates.
These were the freedom, right? I had K, L, M. Those are all the freedoms I have, because they define the coordinate transformation. That's the only thing I'm free to adjust. I assume somebody gave me a G. It's a function of X. And the only freedom I have is to choose a coordinate transformation to change the properties of the metric.
Okay. I was thinking, maybe this is a silly question, but maybe...
No questions are silly.
I don't believe that.
It is absolutely true.
If
sillier the better.
So we're saying that...
Should be funny, too.
6 parameters aren't fixed, so we have three rotations and 3 boosts for the length.
Correct. Yes.
Is that related here?
No, not at all. Not at all. So the way to say it is that I would like to choose coordinates so the metric is eta at a point. It's the first thing. I want spacetime to look Minkowski-like. So the first thing I want to satisfy is that the G mu nu is eta. That I would call a locally Minkowski set of coordinates. Okay. Second thing I can try to do is set the first derivative of the metric to 0. That will mean, so let's write out G prime. Right, so our G prime mu nu of x prime would be G prime mu nu of 0 plus G prime mu nu comma lambda of x prime lambda plus 1/2 G prime mu nu lambda delta x prime whatever, lambda x prime delta. So what I want to know is that for x prime small, I can approximate space-time by Minkowski. So I try to set this guy to eta. And then I try to use the coordinate freedom to set this to 0. Now I'm doing pretty well because now the corrections are only second order in x prime. And so I ask, can I set this to 0? And the answer is no. You don't have enough coordinate freedom to set all the second derivatives to 0. You can set many of them to 0, but you're left with 20 in 4 dimensions. 20 second derivatives you cannot set to 0. And those second derivatives measure how curved the space is. And so if it's curved, then no coordinate transformation will actually make it flat. Only if it was flat. So there's a theorem that if this tensor, this Riemann tensor, if it's 0, you can choose coordinates so that the space is flat. If it's not 0, nothing you can do to make it flat. And the real world is not flat. The universe is not Minkowski space. It's curved. Locally, it looks like Minkowski space, but the whole universe is curved. So I don't know if that helps.
I guess I'm not sure why the not fixed parameters here relate to transformations and these ones don't. Just different things, I guess.
Okay, so here are the parameters we have to play with. There were 16 here. There were in 4 dimensions. And then, this one we have d times d plus 1 over 2, d squared. So these are the parameters we have to play with, right? And what I explained is that here I have more than enough parameters to set g equals eta. I only needed 10, but I actually have 6. It's the opposite. So you have 6 redundant parameters, and that's the Lorentz group.
Oh, okay.
Okay, so I can make space locally flat. But that's a bit ambiguous. Locally flat in which of the Lorentz frames? I've got 6 different parameters describing the frames. So I can make it flat in any one of those 6, in any Lorentz frame. Now I go to the second term and I say, bingo, I have exactly the right number of parameters to make the first derivative the metric 0. There's no ambiguity, there's no extra symmetry, there's no redundancy, it's just right. But when I go to second derivatives, I'm out of luck. I just can't get rid of them. Yeah, it's pretty amazing that, Riemann was this PhD student, and his advisor, I guess, I think was Gauss, said to him, describe a curved space. How do you describe a curved space? Okay, so he realized he needed coordinates, and then he also realized those coordinates are sort of redundant. So now you have to think about the space with all these possible set of coordinates on it, and how do I kind of use up that coordinate freedom in the most sensible way? So the most sensible way is to try to make the space look like flat space as much as you can locally, and then you see what stops you doing that exactly. And it's these second terms, and that's how he discovered the Riemann tensor. So this would just be a clue. There's something in the space stopping me from making it flat. And there's something of these 20 components of the second derivatives. That's the obstruction to making space look like Minkowski space. And then, of course, the reason it's so important is that when Einstein came to write his equation, it relates exactly the Riemann curvature of space-time to the energy, density, energy, and momentum of the matter in the space-time. And we've actually got almost everything we need to write that equation down.